Hi, my name is Andrew McLaren, and I want to help you with titrating acids and bases when they're polyprotic or they're giving off multiple H plus or OH minus ions. The trick to these problems is that you're trying to cancel out the amount of H plus and OH minus. So the math on that we'll go over in just a second, but that's the big picture idea is that you're trying to cancel out these two ions and you need to multiply or divide a number appropriately to get those two ions to cancel out. So when these questions are broadly asking you to titrate, they're asking you to neutralize the two major ions out completely as much as you can. This is going to be going a bit more deep than you may need to for the next couple minutes, but then we'll come back to the math. But if you're trying to understand what's really going on, titration is kind of complicated when you're talking about these polyprotic acids. A lot of them are going to give off hydrogen at different pH values. So like for example, we've got phosphate right here, and it's first giving off hydrogen at around a value of 2, like for that first hydrogen being given off. Then it's fully lost that first hydrogen at around a pH of 5. And then it loses that second hydrogen fully at a pH of about 10. And then that third one at a pH of close to 14. So to titrate a polyprotic acid, because they're weak acids and each step is progressively weaker, you're going to end up getting pretty basic conditions to fully take those hydrogens off. So to neutralize these guys, your pH is not going to be around 7. So you can see also we've got carbonic acid down here. It is fully neutralized or titrated at a pH of about 10 when you've added an amount of base that's pulled off not just the first hydrogen, but the second hydrogen as well. So it's gone through the second Ka for its polyprotic acid. Sulfuric acid is kind of a weird one because the first donation of hydrogen happens at like instantaneously, and then the second one is in pretty acidic conditions. So when you fully titrate it, it is close to like a neutral pH, which is maybe what you might expect for a lot of these problems. But due to them being like pretty weak acids on those second or third titrations, oftentimes this pH is not neutral. So this contrasts a bit with problems that you may be familiar with, thinking about where if you have just something that's not polyprotic but monoprotic, so it gives off one hydrogen, usually that pH that the titration happens at is close to 7. It may not be exactly at 7, it may be a bit higher or a bit lower, depending on the exact strength of the acid, but usually it's around 7-ish for those monoprotics when you've neutralized them or fully titrated them. So if we look at the math on this, we're trying to just basically cancel out the amount of hydrogen and hydroxide that are present. So when we look at this problem here, you can see that the hydrogen is going to be given off 2 times by the sulfuric acid, meaning that when you look at these numbers, you can multiply the concentration times the volume to get these hydroxide ions, those OH minus ions. It's just that volume, I would do it in liters times molarity to get this as actually moles. And then you're trying to then solve that to cancel out the amount of moles of hydrogen that are given off by the acid. To do that, you would need to have 0.27 molar H plus, but because this thing gives off 2 H pluses for every H₂SO₄, then this is going to be half the value for the concentration than you might expect if you were to assume that it was monoprotic. So there's a little bit of algebra that you can do to see that. It's like, okay, well, this needs to be times 2 to get the value. So if I were to have the ratio of the H₂SO₄ to the amount of H plus, there's a 1 to 2 ratio here, meaning if you were to multiply it by 2, you get like that 0.27 molar of the H plus. Because this is really a mole to mole ratio or molecule to molecule ratio, which ends up kind of canceling that out in a sense. So that's the main trick, is that you're titrating these amount of H plus is being given off by the acid and OH minus given off by the base, and needing to do a multiplication or division that's appropriate to cancel out those two ions, so that you're fully taking the hydrogens off the acid, even if it is happening at kind of a weird pH. So you can also see that right here, if you had 1 molar and you were to do an ice chart, you would get 2 molar of this from that being possible to be made. And it's not going to do that because it's a weak acid like fully and completely on its own, but you can pull it forward with a strong base to make that many hydrogens come off of that potentially. We have another problem here where you've got calcium hydroxide being titrated with hydrobromic acid. The same idea holds here, where we're trying to ultimately cancel out the amount of H plus and OH minus. And because we have this calcium hydroxide value of 0.12, if you multiply that by 2, you'd get the amount of OH minus, because each one of those molecules will make 2 molecules worth of OH minus. So it's kind of like you're having to do a little bit of math to appropriately account for the amount of OH minus that are present in the calcium hydroxide. So it really is ultimately this H plus and OH minus that are canceling out. So I oftentimes write those units in for these problems to help me out, just keeping track of what goes where. And in this context, I should be able to get the amount of HBr, because it's a 1-to-1 ratio with the H plus, just by getting the number that we solved for by doing that. It is a bit more complicated if you're not completely neutralizing. You have to think about which one is more present. I'll have a separate video that goes over that a little bit more. But like the main idea on those types of problems is that they don't always cancel out. Your titration curves have them canceled out when you're at this equivalence point, and that's great when you're at that equivalence point, but oftentimes we're not exactly there, and oftentimes you have like a strong acid that's a little bit more than a strong base, and you can see in this context here it's a fairly acidic solution, which makes sense because there's more acid than base, so there's more of that hydroxide or hydrogen H plus than OH minus, ultimately resulting in an acidic solution in a problem like that. Now it does kind of get changed if you've got different volumes as well. You have to account for the volumes. So it is kind of like an ice chart, but you want to think about this ultimately in terms of the moles of these two things that are present. And if you want to really get it over volume, you can do that, but you have to be careful because your final volume will not be those initial volumes that you're working with. So the trick that oftentimes done is in those problems is to just work with the moles and then later account for the volume changes. So yeah, that's the main idea on these types of problems. Let me know if you need more help.